You don't need a pillow for this class.
No, for ethics, for the one after.
Oh, for the one after. Yeah. Friday evening ethics. Riveting. I actually like ethics, but probably not the best subject for a Friday evening class. I don't know what would be a good subject. Probably something in film would be a good Friday evening class. Yeah. Or like bourbon pairings with film or something. I don't know. That'd be a great Friday evening class. I would sign up for that every semester. Yes. Okay. So lecture 6.3, second order systems and transient response. So we did the intro to this chapter and we learned about characteristic responses and how we're going to use them to develop tables of responses to low order systems, and then use superposition and the differentiation property to construct solutions to free response and forced response summations of system responses and mixtures of initial conditions and forced, enforcing function responses. So what we're doing is kind of like mashing up our different solution techniques using these tables that we've developed, and we did that already for first order systems, and we found that, well, not a lot interesting happens with first order systems. They just kind of decay to the new value. If you start off with some initial condition and you let it go, it's just going to decay down, assuming it's stable. If you put in a step input, it's just going to exponentially decay to the new equilibrium value, assuming it's stable. And there were other types of singularity inputs that we didn't look at in depth, like the unit impulse function and the ramp function. We didn't look at those in depth, but they have similarly, I would say, pedestrian responses. They just kind of like decay to new values mostly. So those are first order systems. And we saw an example, and now we're going to do second order systems. We're going to see an example that will actually be Monday that we'll do the example for this. And then recall that at the beginning of this chapter, when we introduced it, we said that higher order systems just look like first and second order systems for the most part, their responses, because usually somebody did bring the tequila. Usually they are just sums. Well, actually, not usually. They are just sums of first and second order system responses. So we can think of them as being like that. So once we've characterized transient response in terms of first order systems and second order systems to different types of inputs, we have a pretty good picture of how most linear systems behave in transient response. Okay. So let's dig into second order systems. I think you guys have done a lot of this before in your differential equations class. It's pretty standard material to cover in a differential equations class. You may have looked at it from a slightly different perspective, but for the most part, you've seen second order systems solved out. So that's what we're doing here. If we look at this differential equation, 6,4, this is what we've got. We've made the first coefficient unity right here, right? So if there was something that was non-unity there and you want it to be in the standard form, you have to divide by that coefficient, right? So if this was 17, you got to divide everything by 17, and now it's 1. Whatever this coefficient is, we're going to break up into a couple different parameters that we'll talk quite a bit about. Zeta is called the damping ratio. It's a dimensionless quantity. And that's going to govern a lot of things for us. And as we'll see, it's going to cover the primary characteristics that we're going to see in the transient response. It's going to also dictate stability. So it's an important quantity. And the other one is the natural frequency, omega n. And that also shows up in the second of these coefficients, I guess third coefficient. So, and then the right-hand side is the forcing function, which for a second order system can have derivatives of the input up to 2 derivatives. So second order derivatives. Systems with two independent energy storage elements, such as those with an inertial element and a spring-like element, can be modeled as second order. So that's sort of, we've seen a lot of them we saw a lot of them in mechatronics, second order systems. So also like an RLC circuit is another example of a second order system that's electronic. I gave a mechanical example there. Good. So if you were to go about solving this problem, you would first develop your homogeneous solution, right? You're going to solve for y, what the output is. You got to find your homogeneous solution, and you do that by finding the characteristic equation, and you find the roots of the characteristic equation, right, to solve for your lambdas that go into your homogeneous solution, right? So say we have two distinct lambdas. You're going to have two solutions because it's the second order polynomial that you'll have emerge as your characteristic equation. So you'll have two solutions. As long as they're not equal to each other, the homogeneous solution for constants kappa 1 and kappa 2 is just the summation of kappa 1 e to the first root t, kappa 2 plus kappa 2 e to the second root t. So lambda 1 and lambda 2 are your two roots of the characteristic equation. And where lambda 1 and lambda 2, if you use the quadratic formula to solve for it, which I did, you will find equation 6.7. Now, we have a lot of ways to go from here, right? So finding the homogeneous solution, assuming you have distinct roots, which is the most common case, it's like an edge case when you have two roots that are the same. And remember, when we have two roots that are the same, we just are going to interpolate a t in there for this guy, right? That's the only difference. But we are setting ourselves up for doing these solutions. And we're going to approach this by finding free response solutions. And then later we're going to find forced response solutions. So the free response solution is going to give us something to go back to. And we will, if we need to know what the free response is for a system, we can just go to the free response solutions that we'll develop here. If you have a system that's got no initial conditions, all your initial conditions are 0, and you have a non-zero forcing function, then you are going to go on to the next section where there's the forced response. If you got a mixture of the two, remember we can use superposition to sum them up. So we're going to develop these solutions for second order systems, free response solutions, forced response solutions in the next section. And then we're going to have them at our fingertips for at least the specific case that we're going to consider, which is these different singularity functions. And so like the unit impulse function, unit step function, unit ramp functions, we'll have those forced responses at least. And then we can use superposition to construct solutions that have, say, multiple inputs that all happen to be these special functions, and or with initial conditions, we can add the free response term in there as well. So that's what we're doing here. We're focused right now on the free response because we've developed our homogeneous solution. And if you want to find the free response, all you have to do is just say, oh, well, my homogeneous solution is the only solution I care about because the forced response solution requires that the input be non-zero or the forcing function be non-zero. And we're not worried about that for a free response. So for free response, apply the initial conditions, and we do so to equation 6.6, and we get y free is equal to the initial condition, assuming that that's the only non-zero one. There's also a y dot of 0. I set to 0. You can work it out. It's not hard to do it, but it's just longer if you want to do that. And the expression just gets a little bit longer. So 6.8, though, is typically what we'll have. And this is solved out for any lambda 1 and lambda 2 that you have as long as they're distinct. Okay? So there are 5 possibilities here. So notice that lambda 1 and lambda 2 have this form of equation 6.7 that can take on a lot of different sort of values here. So the things that we care about our roots of our characteristic equation, remember they're in general complex, right? So you can have completely real, completely imaginary, or some mixture of those two, so complex values of your roots of your characteristic equation. And that's one of the aspects that's going to determine what the transient response looks like, okay? Another thing that's going to really affect transient response is going to be stability. So remember, the stability is governed by the real part of the roots of your characteristic equation. Now, depending on how zeta plays out, this is your real part. If this term over here ends up being real, then it's also mixed in with that. But if you have zeta that's between -1 and +1, at least, then this is your real part. And what you end up seeing is that whenever zeta is negative, so omega n we assume is always positive. It's always positive. Zeta is going to be potentially negative, and if it's negative, then we have a negative sign already here. So we have a positive, what is typically the real part of your solution. And what does that mean about stability? What happens if you have a positive real part for any of the roots of your characteristic equation? Do you guys remember? What does that imply about stability? If we're thinking in the complex plane, what happens if you have roots over here with positive real part?
It's going to explode.
Yeah, this is all unstable over here, right? And transient response, even the mere concept of transient response kind of implies that you're going to have some transition to a steady state, but you don't even get to a steady state if you have an unstable system. So your transient response is an explosion off to infinity, and all bets are off. So that is a very significant characteristic that we want to be aware of.
I like your definition on the second there.
Yeah, the boom.
Yeah.
Yeah.
Pretty good definition.
Yeah, so if zeta is negative, so negative infinity to 0 in that interval, then it's typically very undesirable because your system is going to have variables that explode. And it's very rarely the case that you want that. There are a few special cases, but for the most part, you don't want that. Boom is bad in this scenario. I know boom can be good, but in this case, boom is bad. Okay. I was earlier, in the earlier section, I was saying that, like, we can think of these different values of zeta as being like your different friends, and like if you should bring them to different things that you're going to. So, like, you don't want to bring your unstable friend to the party, okay? You're gonna have a bad time. Like, it's not gonna be good. It's gonna cause issues. So you don't want to bring your unstable friend to the party. Not a great idea. Okay. But a friend that would be a pretty good friend to bring to a party would be an undamped friend. Okay. They're exhausting, but they're pretty good. So what happens is it's gonna oscillate forever, and it will, if you perturb the system from the equilibrium point. So what happens is the lambdas, when zeta is equal to 0, this term goes away. This is just 0 minus 1, which is -1. The square root of -1 is just j, right, our imaginary number. And so our roots are at plus and minus j omega n. So they're right here on the axis, right? Right on the imaginary axis. So we have this marginal stability, and if you perturb it, it's just going to oscillate forever. This is your friend that never wants to go to bed. Bring it to the party, and just stays up and just continues to be ready to go. Exhausting, but fun. Yeah. Okay.
Could you also say it to your imaginary?
Yes. If you think that you have an undamped imaginary friend, you're probably actually the unstable friend yourself. So you're not at the party because no one invited you.
That explains why people don't invite their friends.
Don't worry, no one invites me either.
That's why I don't have any friends.
I'm most people's unstable friend. Okay, so if zeta is between 0 and 1, we have an underdamped situation. So roughly speaking, underdamped is going to oscillate but not forever. Your friend tires out throughout the evening and eventually passes out. This is the best friend to bring to the party. Okay, this is, in my opinion, optimal friend to bring. I need several of these around me to help balance me out. So this is what happens when zeta is less than 1, but greater than 0. So when that happens, this term is going to be negative, but not -1. So there's going to be some imaginary component here. And this term over here is going to be, so zeta is positives between 0 and 1. So the real part will be negative and will be stable. So we're going to be over here in this part of the plane. And that's good. We're going to get some damping out, but we are going to have some oscillation. They'll be fun. They'll be dancing for a while, and then okay, cool. So oftentimes this is where we want our systems to be, underdamped, or so for the underdamped situation, I actually worked out what the roots look like. When you know that it's between 0 and 1, zeta can be switched here. You can factor out a -1. Square root of -1 is j, so we'll just move that out and put it right there explicitly. And then we'll just define this leftover term here as being the damped natural frequency, omega d. So that's what we do in 610. The free response, if you work through it and you rewrite using Euler's formula what the response is in a trigonometric form, you get equation 611, which is, you see this envelope decaying exponential and multiplying a cosine. So you see that this exponential term is going to get smaller, 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 and it's going to multiply this cosine term down to something really small, approaching 0 as time goes to infinity. And you're going to get some oscillation, but that oscillation will damp out. Then, critically damped. Okay, so in this case, the roots of the characteristic equation are equal, and you have this situation where you have to change your homogeneous solution to have another t term in it, right? Because you've got a double root. It's the special case. This is actually something that doesn't happen precisely ever in the real world, right? Because you're always going to be slightly different than perfect roots that are on top of each other. I mean, I should put on the caveat, with macroscopic systems, I mean, if you get down to quantum stuff, then you can have things happen that are like perfect. So I'm going to just say, for engineering systems, you never have perfectly matched roots. However, it's not like this is just like a triviality that we never need to worry about. This is something that is interesting because it's kind of a limiting case. It's going to be the sort of barrier in between two sides. And what's nice is that there's a smooth transition. There's nothing crazy that happens on either side of this boundary, zeta equals 1. So if you have a damping ratio that's like 0.99, you have a damping ratio that's 1.01, your system's going to behave pretty much the same. It'll look critically damped, approximately. So what we have is this response. We have started at an initial condition. It's going to decay to 0, but it's going to be fighting against this linear term, this t, right? So it like almost wants to like do something besides decay to 0, but it gets dominated very quickly. That exponential attunes it right down to 0. So it doesn't oscillate, but it's right on the edge of that, and that's the sort of boundary condition. So then if you continue to increase the damping ratio, I don't know what this friend is. This is like your friend who's like super chill and just like shows up to parties, is the life of the party for a few hours, and then like goes home and bakes. I don't know. And then overdamped is when the roots of the characteristic equation are distinct and real. So this is when zeta is greater than 1. And when zeta is greater than 1, and we go back out to our lambdas, we see that the square root is going to give us it's going to give us a real square root, right? So plus or minus some real number. We're going to have real roots, and those real roots are going to be stable, and they're going to be like this on the real axis, and they're going to be stable. So this is overdamped, and this is going to have a similar decay, but it's just going to decay slowly. It's going to sort of like ooze up. The more damping you get, the more and more it's going to like be like moving through like a thick viscous fluid, and it's getting thicker and thicker, and it's just yeah. It makes that noise too. So let's look at the plot of these different possibilities.
So then, is the overdamped friend that like will just go on?
No. So that was the underdamped friend, or the undamped friend. We'll just keep going on. The overdamped friend, you invite to the party, says he's coming, gets stoned and passes out before he even comes. That's your underdamped friend. And you have to go pick him up at like 1 a.m. because he just woke up and he's hungry. That's your underdamped, or that's what your overdamped friend is like. I've had all these friends.
That makes the story even better.
I'm like thinking of specific people in my mind right now. Okay, so good. So I take us in this graph. So what are we looking at here? We're looking at the normalized output. So I divide all of the outputs, all of these responses by the initial condition. This was in there as a factor in all of our solutions. So if we divide by it, we're going to normalize it all down to be 1 at the very start. Because really it starts off at y0, but since we divided it by y0, it starts off at 1. So great. Then if we have something that's underdamped, so zeta equals 0.1, we're going to have this thing oscillate quite a bit and slowly damp down. This is the time axis, but I also had to normalize time. Dimensionless time is very useful. It's radians per second, so natural frequency is radians per second times seconds, and you just get radians, which is a dimensionless unit, as the unit for time here. And it's useful because otherwise I would have had to do a different graph for every value of the natural frequency, right? It's gonna oscillate at a different frequency. Yeah.
Because the time's going to be delayed as it's more damped, right? Like each cycle is going to take more time as it's.
So what omega n does here essentially is it stretches out time or compresses time. So that is the underdamped. Then like as we increase the damping, so we're increasing the damping from 0.1 to 0.3 to 0.5 to 1. So we just got to critically damped. That's the black line in the middle here. And at critically damped, we finally don't have oscillations, but just barely. Okay? As we increase damping from there to 2, 4, 6, then we get this sluggishness to the system where it responds but slowly. Okay? And those are the overdamped cases. So, yeah. And then if you just keep increasing the damping, then your friend never leaves his house. He stays at home. Never came. Okay. I feel like I've stretched the friend going to the party thing too far.
Well, I think you can get far enough. I think you get to the point where your friend's like just escaping.
Yeah. It's like texting you. I'm there in spirit, bro.
Yeah.
Speaking metaphors all night. Yeah, you're overdamned right now, bro.
Oh man. He'll tell you that like you really gotta watch last night's John Oliver, man. It's like so important. So important. I do actually like John Oliver. Shh. It's my secret. Okay. Good. A lot of times we want our systems that we design to be around zeta equals 1. So maybe it'll be like zeta equals 0.5, maybe it'll be zeta equals 1.5. But usually you don't want a system that's super sluggish. You don't want a system that's too oscillatory. And if you are somewhere in the balance is typically where you're going to want your system. It just depends, though. It depends on your design requirements. The classic example is of an elevator. In an elevator, you don't want typically to oscillate because people don't really like to oscillate very much. Have you guys ever been in an old elevator where it stops at a floor and you like bounce for a second? Yeah. Not the most reassuring feeling ever. Yeah. I don't like them one bit. I do not trust old elevators very much. One of my greatest fears is to get trapped in an old elevator with no cell service and a bunch of people. Terrible. It would be way better if I was by myself. With other people, no. So, we are trapped in the elevator called Earth. It's a big elevator, and there are a bunch of people. Okay. So there are trade-offs, and when you're designing the system, it just depends. Like, so you want to be, but if you over-damped your elevator, it'd take a long time to get to your floor, right? So you'd just be like, slowly get into your floor. You wouldn't oscillate, but you'd also be like, man, I need to get going. It's taking forever. So you want to be somewhere around z equals 1 is like the often the design point, but a little on either side makes sense. And it depends on the type of system you're designing, honestly. So it depends on what you need. But a lot of times around z equals 1 is good. So let's talk about the step response. So we just did the free response, and we really got in depth in the free response. We'll be able to move a little bit quicker with the step response because it's going to look like the free response in a lot of ways, just flipped. Okay, so I'll explain what that means in a minute. But just keeping big picture here, now we're looking at forcing. So we're looking at forced responses. Free responses and forced responses together are going to tell us what happens when there are initial conditions and forcing. We can use the superposition property to sum them together. So if we look at the forced response, we could look at different types of inputs, right? So I'm going to focus on the unit step input because that's the one that typically we use to characterize transient response. It's not a bad idea to use the impulse response either. That's not bad, so we could try that as well. I'm not going to work through that one in this lecture, but I will put the results in the table that we'll talk about. And then also the ramp function is in the table as well. So we'll just do the unit step function and see how that goes. So if we set the forcing to the unit step function and we set the initial conditions to 0, because this is our method, right, we're trying to find the forced response, so we set the initial conditions to 0 when we try to find the forced response. And the roots of the characteristic equation, lambda 1, and lambda 2, if they're distinct, the forced response solution is given in 6.15, which looks a lot like the forced response solution, or the free response solution, right? It looks, this part right here is identical to the free response. But there's this extra offset term. This term is negative, and we have this 1 over omega n squared. So that as time goes to infinity, assuming we have a stable system, this term is going to end up going to 0, and we're going to end up in the final value at 1 over omega n squared. So instead of starting off at some initial condition, decaying to 0, like the free response did, the step forced response is going to start off at 0 and decay to, if it's stable, decay to a final value of 1 over omega n squared. Once again, there are 5 possibilities for the location of the roots of the characteristic equation. Lambda 1 and lambda 2 are all determined by the value of zeta. However, there are 3 stable cases, and then we're going to focus on those: underdamped, critically damped, and overdamped. Same 3 that we looked at before. Well, we looked at 5 before, but we'll look at only 3 now. And we see that we look at what lambda 1 and lambda 2 are, same as in the underdamped case for the free response. And the forced response comes out to be this, which is just what we looked at before. But now we can rewrite the second term in terms of a cosine that is multiplied by a decaying exponential. So we're going to have this sinusoid, damped natural frequency sinusoid, and with an envelope of e to the negative zeta omega n, that's attenuating it down. So that is a response that overshoots the final value. It oscillates about that final value, and then it settles in to that final value of 1 over omega n squared. Well, it never quite gets there. At infinity, it will get to that value. Okay, so the next possibility is critically damped. This is the boundary value, right? So mathematically, we have to treat it a little bit differently, but the solution, the forced response solution, ends up looking a lot like the free response solution, but once again, it's like a flipped version. Instead of starting at non-zero and going to 0, it starts off at 0 and goes to some non-zero value, 1 over omega n squared. So this neither oscillates nor overshoots its steady state value, but just barely, right? Finally, overdamped is the roots are distinct and real, and you're going to get this like sluggish response. It doesn't overshoot at all, but is slow. Okay, so we're going to look at those now, and I plotted the same damping ratios. Notice that we're starting off at 0 instead of the initial condition, and instead of going down to 0 like we did before, we're going to go up to the final value, which is 1 over omega n squared. So I once again normalized the output. So now, oh, typo. This should be forced response. So this is YFO. Oh, didn't catch that in the earlier lecture. I'm like so proud of myself. Aren't you guys proud of me? Thanks, guys.
Should be disappointed in your first class, they didn't catch it.
Yeah, they suck. I'm kidding, guys. I'm kidding. I love it.
That's not a lecture that should be posted.
I think I'm going to post this one. We're having a lot of fun in this one. And the other class is just not as fun as this class. They kind of suck.
That's like a message.
No, I'm just messing with you guys. If you guys out there watching this, you section B2 folks, yeah. I mean, I still feel like you guys can pull it out in the end if you bring me presents. Maybe I'll like you more. Yeah, but not right now. Okay, so So we get this response that goes to 1 over omega n squared. I don't know why I'm on them. They're nice people. They try, you know. Friday afternoons are dangerous. Dangerous. Okay. Impulse and ramp responses. So we could do something similar. We could analyze the impulse responses and the ramp responses too. The analytic solutions are given in the table. So let's look at the table for a minute before we finish up, because I am not going to do the example today. We'll do that on Monday. So what we're developing here are characteristic responses of the second order differential equation that we introduced at the beginning of the lecture with the forcing function f for different singularity forcing functions. So we've got sort of 3 sections. So the first 3 rows are the underdamped case. So I only did the solutions for stable and marginally stable I guess only for stable systems in this table here. So we have the 3 different singularity inputs. So the impulse, step, and the ramp for an underdamped case. If we put in as the forcing function, so as the forcing function, the right-hand side of the equation, not as the input, the forcing function, the impulse, the step, or the ramp, we get these three results. So the last one's a little messy, but not terrible. We had already seen this, so saw this in the equations above. So yawn or whatever. Can you exclamation mark yawn? Is that like an oxymoron? An exclaimed yawn? Yeah. Yeah. Okay. It's like, yeah. It's being like vehemently neutral about that. Or, I don't know, some other turn of phrase that's more clever. Okay. I have a couple minutes to. Okay. So, fun idea that I was talking about with somebody who's in ASME who will not be named. We should start a happy hour, like a Friday afternoon, evening happy hour, right? What would be?
This class.
Oh, well, I mean, we could go after the class to happy hour. Is what I'm saying. I think it would be fun. Oh. Well, I only recommend legal drinking on YouTube, at least. I only recommend legal drinking. Yeah?
No, I like Sonic's Happy Hour. They probably have the best.
Nah.
Really?
Yeah.
What about Taco Bell Happier Hour?
Oh, man, that is good too. Got me with that one.
Well, you came to concert.
We're both good. Solid options.
You guys, your vision of happy hour is just not where it needs to be. It could get so much better than this, guys. Seriously? That's crazy. That's crazy. Okay.
Who is over 21?
Well, not the most, but today's my birthday.
Ah.
Well, I'm 24 now, actually. So.
Nice. Me too. No, I'm not. There was a time, like 9 years ago. Yeah. Okay, so great. Underdamped, critically damped, the solutions are different. Overdamped, the solutions are different. And remember, what do we do with these? These in and of themselves are useful, right? Like they're in the table, like we can look them up. If we happen to have like exactly a unit step input or a unit ramp input, we get these solutions, that's great. But remember, what makes this much more powerful is that we can use these characteristic responses along with superposition and the differentiation property to construct solutions to a bunch of different types of systems. So maybe there are non-zero initial conditions. Remember, these are assuming zero initial conditions, but we can use superposition to add the forced response and the free response together. We can also have maybe a linear combination of like two different inputs that show up in here, and then we could just use a linear combination of the characteristic responses. In fact, 8.15 in your homework this week, I mean, you didn't have to use, you actually aren't supposed to be using the tables in the homework that you're doing right now, but it's fine if you did, I don't care. But you're seeing exactly that, where you have a Dirac delta function as one of your inputs, seeing a unit step function as the other input, and then it wants to know what the solution is for the linear combination of those two. So you have to use superposition for that. So you're doing this already. When you mix that together with the tables that you now have for first and second order systems, it becomes even easier to wield those weapons. You don't wield, I was going to say you wield those tools, but I don't think that's what you do with tools. What do you wield? You wield weapons.
Wield a sword. Yeah, sword.
You wield swords.
I think sword specifically.
I got my first tarot reading last night, and
It's a weird thing to do on a Thursday night.
it is. It was my first, so it was weird for me too. But I got a three of swords or something. 9 of swords. 9 of swords, which is apparently like the scariest card to get. But I kind of liked it. It was kind of fun.
What is it?
I interpreted it to mean that it was like part of the like past thing, so maybe it's like passing on all of my wild parties and putting people to death is moving on now into my past. So maybe I'll be done. I'll be done with my my murders and stuff, and yeah. No more maiming myself accidentally.
Okay, so there's
It's tempting to do it on purpose.
There's two different swords. 9 of Swords is a minor arcana card. Lord of Cruelty
Oh, that sounds nice.
is a native sign that has go turn leave. It being turned can be instigated by others as might come up to show that one is cruel to someone nearby.
Uh-oh.
The first class.
Sorry, guys.
Swords is highly sensitive to conflict, so you may have gotten a 5 of Swords.
Oh. Yeah, now I think that I got a photo of it. I'll have to go back and review this. I'll get this straight for next week, okay? What that meant and how to go from here. Okay, guys.
7 of Swords reveals issues of breaking free.
And I love you, morning section. So sorry.
He doesn't. Don't listen to him.
Okay.